So with this, we can move on to the another type of dimensionality reduction method, which is multi-dimensional scaling, MDS, multi-dimensional scaling. So multi-dimensional scaling, the term metric multi-dimensional scaling made its first appearance in 1938 in Richardson's multi-dimensional psychophysics. Of course, several people before Richardson, including Boyden 1933, had used the concept, although they don't call it multi-dimensional scaling. So Boyden, a biologist, used the technique to create models for relationships between common amphibia. So now let's see the definition and explanation of multi-dimensional scaling. Multi-dimensional scaling is a dimensionality reduction technique used to visualize and analyze the similarity or dissimilarity between data points in a high-dimensional space. MDS aims to find a lower dimensional representation of the data while preserving the pairwise distances. Pairwise distances or similarity or dissimilarities between the data points as much as possible. The lower dimensional representation allows us to visualize the data and gain insights into its underlying structure. So now let's look into the history of MDS, multi-dimensional scaling, MDS. The multi-dimensional scaling was first introduced by mathematician and psychologist Torgny Soberg in 1963. This concept was further developed by psychometrician Roger Shepard and others. So MDS has since become a popular technique in various fields, including psychology, marketing, ecology, and data visualization. So now let's look into the few important aspects of multi-dimensional scaling. The first one is assumptions. What all assumptions we have to consider before you apply multi-dimensional scaling for your data set. So the first one is metric data. Metric data. MDS works best with metric data where the distance between the data points is meaningful and interpretable. For example, MDS is suitable for data measured on a scale with a clear numerical interpretation such as Euclidean distances. And the second assumption is symmetric similarity or dissimilarity. Symmetric similarity or dissimilarity measures used in MDS should be symmetric. That is, the distance between the data point A and B should be the same as the distance between B and A. This is very important assumption. And the third assumption that we have here is stability. MDS assumes that the similarity or dissimilarity measures are relatively stable and consistent. Now it's time to look into the applicability part of it. So our applications, MDS is applicable to various types of data, such as psychological data. It can be used to analyze and visualize the psychological similarities or dissimilarities between individuals based on questionnaire responses. And marketing research, MDS is used to understand consumer perceptions and preferences for products or brands. And the third one is ecology. MDS can be applied to study the similarity or species in an ecological community based on environmental characteristics. So now let's look into the mathematical aspect of multi-dimensional scaling. So the core idea of MDS is to represent data points in a lower dimensional space such that the pairwise Euclidean distances in the lower dimensional space are as close as possible to the original dissimilarity or similarity measures between the data points. So let's take given, so the important aspect, the main thing to be done before you apply multi-dimensional scaling objective function is classical MDS uses Euclidean principles to model data proximities in geometrical space, whereas where distance d sub ij between points I and j is defined as this. So d sub ij is equal to square root of summation of x sub I minus x sub ja whole square. So here x sub I and x sub j specify coordinates of points I and j on dimension on dimension A respectively. So next, what we have after calculating the distance d sub ij between the points x1 comma x2 or x sub I and x sub j, what we have to do, that's what is the next mathematical equation. So given a set of n data points x1 comma x2 and so on xn, MDS multi-dimensional scaling aims to find a lower dimensional representation y sub 1, y sub 2, y sub 3 and so on y sub n in k dimensional space where k less than n, such that the pairwise Euclidean distances in the lower dimensional space minimize the discrepancy with the original dissimilarity or similarity measures. So, hence what we get is the objective function. The objective function for MDS can be expressed as minimize some double summation of d sub ij minus modulus of y sub I minus y sub j whole square. So here where the d sub ij is the dissimilarity or similarity measure between the data points xi and xj that we have calculated with above formula Euclidean distance, and the modulus of y sub I minus y sub j is the Euclidean distance between their lower dimensional representations of y sub I and y sub j. So now it's time to see one example so that we can have a clear cut understanding of how this multi-dimensional scaling works. Just to understand the mathematical aspect, I'm going to give you one example. Let's consider a simple example with a two-dimensional data set. We have only two dimensions in the data set. It's nothing but the two columns, simple two columns, or two features where the data points x1 comma x2 comma x3 comma x4 comma x5 and so on xn are represented by two columns x and y. We will apply MDS to find a lower dimensional representation y sub 1 comma y sub 2 comma y sub 3 and so on y sub n in one dimensional space k is equals to 1, while minimizing the discrepancy with the original Euclidean distances between the data points. So to do that, we need to understand more about the data set that we have. So in this data set, we have total 5 data points. You see that data points are 5 or 5 records. or 5 observations. So our n is equal to 5, and we want to find a one dimensional representation. That's our records are n, which are 5, and I want to find a one dimensional representation. So where k is equal to 1. So n is equal to 5 and k is equal to 1. That preserves the pairwise Euclidean distance between the data point as closely as possible. So now let's begin our action with the step 1. Step 1 is to calculate the pairwise Euclidean distances d sub ij. Okay, d sub ij. We need to calculate the Euclidean distances between each pair of data points. For example, the distance between x1 and x2 is d sub 1 2. That's all. So this is x1.1, x2.2, x3.3, x4. So now the distance between the pairwise Euclidean distance, we call it the pairwise Euclidean distance between the point x1 and x2 is called as a d sub 1 2. D sub 1 2, which is nothing but obviously y2 minus y1 all square plus x2 minus x1 all square, square root of y2 minus y1 all square plus x2 minus x1 all square. The same formula we'll use. It's because it's an Euclidean distance. So how much I got was 2.24. So d sub 1 2 is 2.24. Similarly, I have to calculate d sub 1 3, d sub 1 4, d sub 1 5. Then d sub, once this is done, then d sub 2 1, d sub uh, 2 2, those are remain same. So d sub 2 3, 2 4, 2 5. Then d sub 3 4, 3 5. Then d sub 4 5. These are the remaining distances we have to calculate, because here we think the assumption is that symmetry, data is symmetry. That means d sub 1 2 and d sub 2 1, it remains same. Okay, or d sub 1 3 or d sub 3 1 remains same. That's the assumption we have considered. If it is not the case, then this multi-dimensional scaling reduction method can't be applied to the respective data properly. So that's why assumptions are very important before you applying it. So hence we have calculated the respective Euclidean distances, pairwise Euclidean distances. Now let's time to move on to the step 2. So step 2 is nothing but apply MDS to find lower dimensional representations, which are y sub 1, y sub 2, and y sub 3, and so on, y sub n. So in this example, we want to find the one dimensional representation. So k is equal to 1. So let's assume the lower dimensional representations are y sub 1, y sub 2, y sub 3, and so on. Y5, Y sub Y, Y sub 5. Okay. So now step 3, minimize the objective function. So now we minimize the objective function using the respective formula or respective objective function. So the objective function represents the discrepancy between the original pairwise distances d sub ij and the Euclidean distances in the lower dimensional space, that's y sub I minus y sub j. So the MDS algorithm iteratively adjusts the values of y sub 1, y sub 2, y sub 3, y sub 4, y sub 5 to minimize the objective function while preserving the relative distances as closely as possible. The result will be a one-dimensional representation of the data points that best represents the original pairwise distances. So keep in mind that in practice, MDS is typically used for higher dimensional data sets where visualizing the data in 2 or 3 dimensions is challenging. In those cases, MDS can be a valuable tool to project the data into a lower dimensional space while preserving the relationships between data points. So now let's move ahead with our understanding of multi-dimensional scaling. So Obviously, we have seen the mathematical parts of it and we have understood the mathematical parts of it. Now it's time to look into the algorithm working process. That's what we are going to see. So algorithm working process, the typical steps involved in MDS are as follows. The first one is define dissimilarity or similarity. Choose an appropriate dissimilarity or similarity measure to quantify the pairwise distances between the data points. Common choices include Euclidean distance or correlation distance or rank based measures like Spearman's rank correlation. Then step 2, compute distance matrix. Compute the pairwise dissimilarity or similarity matrix based on the chosen measure. And then step 3, define the number of dimensions. Basically k, determine the number of dimensions k for the lower dimensional representation. Usually k is chosen to be less than the number of data points to achieve the dimensionality reduction. Then it's time to apply MDS algorithm. Apply the MDS algorithm to find lower dimensional representation that minimize the discrepancy between the pairwise Euclidean distances in the lower dimensional space and the original dissimilarity or similarity measures. And the last step is to visualization. Visualize the lower dimensional representation to gain insights into underlying structure of the data. So, in addition to that, now it's time to see some of the real life examples where we can leverage the power of multi-dimensional scaling, which is the first one is psychological studies. MDS, of course, if you work on a projects, data science projects which are related to the psychological field, then obviously you have to go for MDS. So MDS is used to analyze and visualize the perceived similarity or dissimilarity between various psychological attributes such as personality traits or attributes based on the survey responses. And marketing research, MDS is employed to understand consumer perceptions and preferences for products or brands. By visualizing the data in lower dimensional space, marketers can identify clusters of similar products and tailor marketing strategies accordingly. Then the third one, ecological studies. MDS is applied to analyze the species similarities or dissimilarities in ecological communities. It helps ecologists understand the relationships between species based on the environmental characteristics or habitual preferences. Hence, in summary, multi-dimensional scaling MDS is also a powerful dimensionality reduction technique that transforms high dimensional data into a lower dimensional representation while preserving the pairwise distances between the data points. It finds application in various fields to visualize and analyze the underlying structure of data, leading to valuable insights and informed decision making.